Okay, good morning, everyone. I've talked a lot about the kind of black hole astrophysics and science you can do with LIGO and LISA, pulsar timing arrays, but I thought I'd give some of the important but kind of auxiliary science you can do with pulsar timing arrays as well. So we're always going to be focused on supermassive black hole binaries as the main target population, but there are other signatures of gravitational waves and also not gravitational waves in the nanohertz band. So we could be sensitive to a background of primordial gravitational waves. So these are gravitational waves from the very early stages of the universe. Gravitational waves from a network of decaying cosmic strings, and I'll briefly explain what those are again. We could be sensitive to some dark matter signatures within the galaxy. That is not a gravitational wave signature, but it does cause a potentially measurable signal in the pulsar-timing array time series. And we're also very sensitive to solar system dynamics, and this has actually caused us a lot of recent annoyance because we thought we were accurate enough in our model of the solar system, but it turns out that we don't know the position of the solar system barycenter very well, and that is something we need for an intermediate stage in pulsar timing. So we need to correct all of the arrival times of the pulses to the solar system barycenter, and then correct from there back to the pulsar, and that's sort of our chain of corrections for the arrival time of the pulses. So if we don't know the position of the barycenter very well, then that's going to be off, and we're going to introduce some errors into the gravitational wave inference. So first of all, primordial gravitational waves, these occur naturally within the inflationary theory of cosmological expansion. You probably all know about what inflation is, but it was proposed maybe 35 years ago and conceived of maybe even earlier to explain several perceived problems in the hot Big Bang model. There was the flatness problem, the horizon problem, and then the magnetic monopole problem. And inflation is this period of exponential expansion that happened within 10 to the minus 35 to 10 to the minus 33 or 2 seconds after the Big Bang itself. So the universe went from, it increased in size by a factor of maybe 10 to the 40 or 10 to the 45. So the flatness problem asks why the curvature of the universe is really, really, really close to zero. The horizon problem asks, given the CMB and given how isotropic it is, how is it that in the early universe, all of the regions of space-time were in causal contact and were in thermal equilibrium? How did they send light signals to each other if the universe has seemingly expanded faster than the speed of light? And the magnetic monopole problem asks why there are no magnetic monopoles. Certain grand unified theories predict quasi-particles, which are heavy and stable, and one of these is the magnetic monopole. But why is it that we don't see those? Why do we not see isolated north or south particles? So inflation naturally drives space-time curvature to zero, so it flattens it out completely. The horizon problem allows for all regions of space-time to have been in causal contact before the inflationary expansion, and then drives them apart very fast. So the universe could have been in thermal equilibrium before inflation, and then inflation drives it all apart to give what we see today. So you get an exponential expansion of the scale factor, A, where H star is the Hubble expansion rate during inflation. And the magnetic monopole problem is explained by, this is a very cartoon idea of why it's solved, but inflation would drive all of the distribution of magnetic monopoles apart so quickly and so fast that the observed density would be zero. So inflation is not really saying that they don't exist, it's just saying that they would probably not be detectable because their observed density is zero. I'm sure there are many people in the audience who know more about this than I do, so if that's too cartoon of a picture or you know more about this, then please jump in. I don't like it either, but this is what I read yesterday. That is true. That is true. So does anybody else have a better explanation of why magnetic monopoles don't exist? Or why inflation drives them apart? Yeah. Mm. Well, I mean, yeah. 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 You would have to tune your grand unified theory to not produce magnetic monopoles. And I think they are, the problem, as I understand it, is that lots of these theories predict just particles which aren't seen in nature. So although they combine all of the forces, they give a lot of spurious particles. Yeah. Yeah. Mhm. So you think it's easy to tune inflation such that it doesn't produce magnetic monopoles? Mm-hmm. Yeah. Right. Mm. Still speculative. Yeah. Yeah. Uh, no, I think the idea is that, um, well, my understanding is that the decay of the inflaton field in the standard model particles also produces gravitons, and that's where the primordial gravitational waves are coming from. Mm-hmm. 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 Well, this is something I've always wondered. So, are the primordial gravitational waves coming from a different mechanism than the standard model particles? They are coming from a different mechanism. Okay. So it's not that the inflaton field will decay into lots and lots of particles, but not gravitons. Yeah. Mm-hmm. Okay. So to answer John's question, you can't get primordial gravitational waves without inflation. Mm-hmm. you can have gravitational waves from bubble collisions when the universe goes through a phase transition. Mhm. So it's just lots of wiggle room to explain results. Okay. Hmm. Okay. Well, Ricardo's already answered this question. How do we get gravitational waves from the early universe? Yeah. Mhm. Yeah. The flat spectrum is the prediction. Okay. We're potentially sensitive to that. So I'll show later that the spectral index of the characteristic strain spectrum can be sensitive to NT, and also the equation of state in the early universe. So some combination of those could be constrained. Okay. Now the cartoon picture I got was from Bruce Allen's lecture course in 1997. Um, it starts off with a quantum mechanical pendulum, which can never be at rest. It's always doing 0-point fluctuations around the midpoint of the swing. If you slowly increase the length of the string in the pendulum, then it'll go through some adiabatic change in its configuration. So you're changing the length of that string over longer timescales than it takes for it to oscillate. And that causes an adiabatic change, and it remains in its ground state when it moves into its new configuration. But if you rapidly increase the length of the string, such that it's non-adiabatically changing its configuration, then you will actually create an excited state in the new configuration. So it no longer remains in its ground state. When you rapidly increase the length of the string, as you would in inflation, you would rapidly change the configuration. You'll be moving into an excited state of the new configuration. So you'll produce quanta. So that's how you make standard model particles. The idea that inflation is rapidly changing the configuration of the universe, and you'll get a decay of the inflaton field into standard model particles. And you'll also get some gravitons from there, but most, as Ricardo has kind of just explained to me, most will come from the expansion of vacuum fluctuations. So gravitons are included in the decay of the inflaton field. When the universe has gone through inflation, it'll be in an excited particle state. It'll decay, produce all the standard model particles in this period known as reheating. You'll get some gravitons, but most of them will come from inflationary expansion of vacuum fluctuations. Yeah. Oh, so there'll be the subdominant particles produced in this decay. Right. Yeah. Yeah. Right. But do you start off with really, really heavy standard model particles, and then it just decays into conventional standard model particles? Mm-hmm. Mm-hmm. Right. You could just have it whichever way you want. Okay. Regardless, this is how you get some gravitational waves in the time of inflation. So within inflationary theories and also just within the early universe, you'll get some background of primordial gravitational waves. One way we can probe this is with pulsar-timing arrays in the nanohertz band of gravitational waves. We usually parameterize the characteristic strain spectrum of gravitational waves in the pulsar-timing band as some sort of power law. You've got a dimensionless strain amplitude and then some spectral index behavior. For primordial gravitational waves, the spectral index can be written as a combination of NT, the primordial tensor spectrum, and also the equation of state in the early universe. Now, inflation predicts that this should be basically flat, so NT should be close to zero, or almost, or essentially zero. And then in the early universe, if you've got a radiation-dominated universe, then the equation of state should be a third. So you rearrange all of this, and I think Lena did a lot of work on this, predicting that this should obey a power law close to f to the minus 1. So this is showing from the Grav 9-year data set our strain upper limits. So the upper limit on this, this dimensional strain amplitude for different values of alpha, which is then packaged into a different type of spectral index. So this is really the spectral index of the power spectral density of the timing residuals. So if we just take the pulsar time series and we work out the power spectral density of that, that'll have a power law form, which is gamma equal to 3 minus 2 alpha. So if we plug in alpha equals minus 1, that's going to give gamma equals 5. So we just kind of look up at what our upper limit was from that analysis of the data set, and that gives us something close to 8 times 10 to the minus 16, which can give us a 95% upper limit on the energy density of gravitational waves in the primordial component. So gamma, yeah, let me make this clear. So what we're directly sensitive to is the power spectral density of the time series. So if you look at the covariance between some observations, say that the time delay at time I, the time delay at time j, then you can so this is the Wiener-Kinchen theorem. It converts you, it does a cosine transform of the power spectral density of the timing residuals to give you the time domain covariance between the residuals. So any sort of low frequency read process, like a gravitational wave background, will induce correlations between your observations over very long time scales. So this is related to the characteristic strain spectrum through this. Okay, so that's the power spectral density of the time residuals. That's the characteristic strain spectrum of the gravitational waves. And if you rearrange all that, you'll get something, you know, if you just plug in the characteristic strain spectrum having a power law form, you'll get f to the minus gamma. Yeah, that's a terrible gamma, but. The f cubed. That comes from the, it's the transfer function from the overlap reduction function. So you get an f cubed there. Well, you actually get you get 2 f's, and you also get a factor just from the Fourier transform, I think. Yeah. Yeah, because I mean that's the relationship there. So if you've got the characteristic strain spectrum being a power law f to the alpha, f to the -1, you square that, you get something which is flat. Yeah, so they're all related. It's just that we're directly sensitive to this quantity in the data analysis, and then we use these relationships to get upper limits on the characteristic strain, and then omega GW. So this is one way of attacking the primordial component of gravitational waves. The benefit of doing this with gravitational wave analysis rather than doing this with the CMB is that we're directly sensitive to the earliest times in the universe with gravitational waves. Whereas the CMB has this wall of 300,000 years after the Big Bang that we can't see beyond. Okay, and as well as gravitational wave experiments, you could be sensitive to this, to these gravitational waves just through the polarization of the CMB. Primordial gravitational waves would induce a curl mode in the polarization of the CMB. So it would have, if you produced a polarization map of the CMB, it would have these sorts of features in it. And in March 2014, BICEP2 claimed that they measured a curl mode component, which they interpreted as potential evidence for primordial gravitational waves, but subsequent analysis showed that this was completely consistent with their analysis being contaminated by dust in the Milky Way. So they used a preliminary or some suboptimal map of the dust content of the Milky Way from Planck, and yeah, they got a spurious signal in the curl modes. So they're still working on this. They're going to, I'm sure they'll continue to produce new experiments which will look at the polarization content of the CMB. But one benefit that pulsar-timing arrays and other gravitational wave experiments have is that we're not going through an intermediary. We're not going through the CMB. We're just going directly to the gravitational waves themselves, and we're directly sensitive to them. Okay, were there any questions about primordial gravitational waves that Ricardo can answer? Okay, well, let's go into cosmic strings, which are probably even more speculative. This is a snapshot of a numerical simulation of cosmic strings. This would be a Hubble volume, and within the Hubble volume you have these very long infinite strings which don't close within the Hubble volume, but when they intersect, when these large infinite strings intersect, they can chop off smaller sections, small loops, which vibrate and decay via the emission of gravitational waves. That's what these kind of red small dots are. So they're topological defects in space-time during a phase transition in the very early universe. You can consider topological defects in crystal phase transitions, or maybe even more cartoonish, cracks forming when ice melts. They exist within this quantum field theory, but you can also get them in superstring theories, where you have the expansion of fundamental string objects to massive cosmological scales. So the width of these objects is basically just a Planck length. So they can essentially be treated as one-dimensional objects, just permeating the Hubble volume. Like I said, infinite strings will permeate the Hubble volume. From numerical simulations of cosmic string networks, you get about 50 of these infinite strings throughout the Hubble volume. If they do intersect in all dimensions, that has to be 3 for regular strings, but 10 or whatever the current number of dimensions is for M theory, then you get small loops chopped off. So there has to be some, each string will have some intercommutation probability. So they'll interact with each other, and they will exchange some information, and then that will chop off a smaller piece of the string. One thing that makes a string network almost fractal is that they scale. The statistical properties of subvolumes of these cosmic strings looks exactly the same. So you can just take a small part of this Hubble volume, and the statistical properties will be the same as the entire volume. Small loops will radiate and decay through gravitational wave emission, and that's important. When I think Vilenkin was doing these calculations in the 80s, cosmic string loops could decay only via the emission of gravitational waves. Maybe there are some more developed theories which could have them decay through other mechanisms as well, but gravitational wave emission is always going to dominate. And that's because the string tension, so the tension of these objects, is comparable to the mass per unit length of the string. And that's much, much different from what you would get by just the string that you would wrap a package with. In that case, the string tension is very, very small compared to the mass per unit length. But because these have a tension which is huge and comparable to the mass per unit length, they vibrate relativistically, and they decay then through the emission of gravitational waves. Okay, and again, we're sensitive to cosmic string networks and the decay of these cosmic strings through gravitational waves in the pulsar-timing band. This is showing two regions that we've excluded in parameter space for cosmic strings. This is the intercommutation probability, so the probability that when two strings intersect with each other, that they'll cut off a smaller cosmic string. This is the string tension, where mu is the mass per unit length, and g is Newton's constant. And then alpha is related to the size of the cosmic strings when they form. So for an intercommutation probability of 1, we can rule out certain regions of the string tension parameter space to very high accuracy. And currently, pulsar timing arrays are better at constraining the parameter space of cosmic strings than any other cosmological probe. So this constraint and also the combined constraints of the entire parameter space are currently better than Planck plus the Atacama telescope plus the South Pole telescope combined. So if you combine all of these very sophisticated cosmological experiments, pulsar timing arrays are still able to put a limit which is about 4 times better than the combination of those. So pulsar timing arrays are currently the best bet at constraining that parameter space. Sure, this is within a particular model of a cosmic string network. It's all kind of discussed a bit more in detail in the paper, but it was from recent numerical simulations by, I think it's the Blanco-Pallado simulations, maybe from 2 or 3 years ago. Yeah, I don't know any more than that, I'm afraid. So some models of cosmic string networks do admit a power law form for the characteristic strain spectrum. And this could be related to something around alpha, which is equal to the minus 7.6. So that's going to give a gamma, which is roughly 5 1/3. And if you just track up what the upper limit on the strain amplitude is for a gamma of 5 1/3, you get that the upper limit is about 6 times 10 to the minus 16. And then what we did was convert this into these constraints. So really this is just a repackaging of the previous constraints, which, as I said, are 4 times better than the combination of conventional cosmological probes. Okay. Now, cosmic strings are very speculative. I don't think there are really good understandings if they actually exist or not, but I don't know too many more of the details apart from what we've studied here. Yes, yeah, the primordial. Yeah, the question is how well can we resolve the, yeah. I think it's going to be a long, long time before we're able to resolve that, if at all. Because the supermassive black hole background is going to dominate anyway. So you're going to be looking for a very weak component. You look perplexed. What are you going to say? I don't think so. So the other discrepancy would be that a population of supermassive black hole binaries could be eccentric as well. So that would induce correlations between the frequency bins, because you have the same binary contribute to multiple frequency resolution bins. Whereas primordial, I think, would be stationary, and also for cosmic string networks, that'll produce a stationary background. So maybe if you could tease out any non-stationarity in the signal, you could look at these other components. Mm-hmm. 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 Well, yeah. I mean, we're nowhere near 10 to the minus 15 yet. Yeah, yeah. It must be. I think it's related to one of the earliest models, but they don't vary a lot, as I understand them. Is there anyone in the room who knows more about numerical simulations of cosmic strings? Okay, well then I can get away with saying that they're just 50. No, I think there's too much degeneracy in the parameter space. We inevitably, when we do these constraints, we have to fix something, and I think that's one of the things that's fixed in the simulations. Okay, now dark matter. This is something we've been looking at recently, and it's very interesting because it's not actually a gravitational wave signal. Well, everything I've talked about before is something that's producing gravitational waves, and that we're being sensitive to through the changing of the proper separation between the Earth and the pulsar. But this is a particular theory of warm dark matter, which avoids certain problems in the cold dark matter theory of structure. Cold dark matter predicts that you'd have much more structure on subgalactic scales than is actually seen. So warm dark matter could actually mitigate this, and so there are lots of theories of this warm dark matter. One such theory is that you have an ultralight scalar field. That'll produce an oscillating in time pressure within a galactic halo, and that'll then produce oscillations of the galactic gravitational potential. So this oscillating galactic gravitational potential is going to change the arrival rate of pulses from the pulsars, but it's not a gravitational wave signal, right? So it is going to produce a sinusoidal time delay behavior in the pulse TOAs. In a single pulsar, that'll look like a binary signal, but there'll be no antenna pattern modulation across the sky. So if you actually did this coherently across multiple pulsars, then it will almost look like what a clock uncertainty does, because it's going to affect all pulsars equally across the sky. Now that's the current thinking, that there's no antenna pattern modulation, but there must be some modulation across the sky, just because you'd imagine that in certain parts of the Milky Way there'll be a larger density of this warm dark matter. So depending on the position of the pulsars with respect to the density of the dark matter distribution, there must be some modulation. So if we see a larger signal in a particular part of the sky, then that could be us being sensitive to an overdensity of this warm dark matter. So it's pretty interesting. We've only recently started to look at this, the idea of constraining the parameter space of this warm dark matter. But like I said, we have to build a completely different model because it's not a gravitational wave signal. We're not getting this antenna pattern behavior. So the amplitude of any time delay that we see in the pulsar timing data is going to be proportional to the time-dependent part of the galactic gravitational potential. So this would be the parameter which I'm going to show you in the next plot. It's psi sub c, and that's just the amplitude of the time-dependent part that the warm dark matter is causing. And interestingly, the frequency of any signal we see is going to be proportional to the particle mass of the warm dark matter. So to calibrate 5 nanohertz signal or a 5 nanohertz feature in the pulsar timing data corresponds to roughly a particle mass of 10 to the minus 23 electron volts. You can't think about it like a stochastic signal, so you could just look for a signal frequency spike in your power spectral analysis, but that's kind of ignoring all of the coherent features across different pulsars. So you really want to phrase it as a deterministic signal analysis. And very recently, some people have come up with models you can just write down and incorporate into your pulsar timing analysis pipelines and run a deterministic analysis, which will constrain psi c and also allow you to get these constraints on psi c as a function of the mass of the particle. So the way we'd actually run this is you fix the frequency of the feature in your pulsar timing analysis. You'd get an upper limit on any sort of sinusoid that's at that frequency, and then you'd convert that to a constraint on psi c, and then your frequency is just simply related to the particle mass. But for a first approximation, since we haven't done this deterministic analysis yet, you can just treat this as a narrowband spectral process, a stochastic process, and we can just take our existing gravitational wave background upper limits and convert everything to the relevant dark matter parameter space. So like I said, you can just simply convert the characteristic strain upper limit into a constraint on size c, and then you change your x-axis from frequency into the particle mass of the warm dark matter. So this is something that takes about 2 minutes, going from the Nanograv 9-year limit paper to this dark matter parameter space. So like I said, it's easy to convert from the frequency. So this is the observed frequency of processes in the pulsar time series. So really, this plot started off as per frequency upper limits on the characteristic strain. And I've just converted the x-axis, the frequency, into the mass of the particle, and then converted the y-axis, the characteristic strain, into the amplitude of the time-dependent component of the galactic gravitational potential. Now this is a new theory, so we don't know how competitive this is with anything else, because it might be the only thing that can probe this. Sure. Mm-hmm. Mm-hmm. Yeah. Oh yeah, I totally agree that I've started off at sound physics and then gone downwards in speculation. So what do you mean we've arbitrarily suppressed the mass? You said we've arbitrarily suppressed the mass. Yeah, yeah, yeah. Mm. 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 Okay. Oh no, yeah, we're definitely taking it with a pinch of salt. You know. Well, yeah, it's so the relevant paper is Khmelnytsky and Rubikov 2014. We should talk about this because we're thinking about trying to actually constrain this for the upcoming Nanograv limit paper. So if there are obvious flaws in the theory that make it just not viable and we shouldn't even take it seriously, then it'd be good to know. Mm-hmm. Okay. Okay. Yeah, yeah. Oh, right. Mm. Yeah. I, I don't think it's a stupid. But if Big Bang nuclear synthesis already puts a stronger constraint on this parameter space than pulsar timing does, then there's no point in us trying to explore it. Mm. Okay. Mm-hmm. 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 You don't actually need to invoke it to solve the satellite problem. Okay. Mm-hmm. Mm-hmm. Okay. It's interesting. But this is us very much just going after low hanging fruit. It was, you know, yeah. The warm dark matter? Oh, okay. 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 So then this is maybe a bit outdated already. Oh, right. Right. Yeah, the ultralight. I think it's an axion particle. Um, did you manage to take a look at it, Ricardo? Does it look plausible? Yeah, I'd be interested to hear if you actually think it's viable and worth our time, because it's low hanging fruit. It's so easy to go from the existing constraints for pulsar timing into the parameter space. So it would be nice to do. Yeah, and it's a theory it's a model that's been published in the literature, so we should be able to comment on it. And I think it's the only thing that we have to probe that's not actually a gravitational wave signal. So, yeah, yeah, yeah. Any other comments on dark matter before I move on to solar system stuff? Okay. Um, Now this is something that I've been spending a lot of my time over the last 6 months studying, and it's the sensitivity of pulsar timing arrays to solar system dynamics. Um, so our sensitivity comes about through the chain of corrections we have to do in going from an observatory pulse measurement, tracing all of that back to the actual emission at the pulsar itself. So we'll measure some pulses at an observatory on the Earth. We'll then have to correct that to the geocenter. Then we have to correct for the light travel time from the geocenter to the solar system barycenter. That is our sort of quasi-inertial frame that we reference everything to. And then we trace that back actually to the barycenter of the pulsar system. If it's in a binary system, then we have to take into account that there'll be some binary dynamics, which will shift the center of mass away from the pulsar itself. But then we have to trace the pulse actually back from the pulsar barycenter to the pulsar itself. So this huge chain of corrections at the moment seems to be dominated in uncertainty by the Roemer delay. And that's this, the classical light travel time between the geocenter and the solar system barycenter. So the emission at the pulsar is going to be related to the observed pulse arrival time at the telescope through the Roemer delay. Then there'll be interstellar medium propagation delays, and then you'll have the pulsar barycenter delay. So the Roemer delay is just going to be the projection of the observatory position vector onto the pulsar position, essentially the pulsar barycenter position vector. So that's going to be the classical light travel time between the geocenter and the barycenter. And this observatory vector is just going to be some large component from the solar system barycenter to the Earth barycenter, and then some small offset from the Earth center to the observatory. But this part here, the solar system barycenter to the Earth barycenter, that requires us to know the position of the solar system barycenter to incredible accuracy. So the kind of time delay induced by gravitational waves might be of order tens of nanoseconds. That could be of order tens to 100 meters. So we need really to know the position of the barycenter to very high accuracy. And if you make a small error in the position of the barycenter, that's going to induce an error in the Roemer delay, which will show up in your time and residuals as this error term. So you'll have some time-dependent vector, which is the offset between the true barycenter position and your model of the barycenter position. If that uncertainty, if that error is coming from, say, an error in Jupiter's mass or an error in Saturn's mass, then this kind of signal will show up as a periodic signal with the orbital a frequency comparable to the orbital frequency of Jupiter or Saturn or the other dynamical object that the error is coming from. So just to give you an example of the kind of differences in the Römer delay coming from the different models of the solar system we use, this is the difference in the Römer delay in nanoseconds between different models of the JPL solar system ephemeris. So the JPL solar system ephemeris is kind of the standard ones that we use. They periodically release new fits to spacecraft data, to ranging data. They update the masses of some of the planets that they use. And there can be quite significant differences between them. So starting off at DE 421, which was released in about 2008, I think, going to DE 430, they've updated Jupiter's mass, and then going forward, they've updated Saturn's mass. As they've gone on, you've added new Cassini data. The new releases that will come out in the next year or so will include new Juno data. And every time it's kind of iterative correction process where they add new data, they weight the data differently depending on where it's coming from, and that's kind of, it's a bit of a black box how they do that. But they'll weight it differently, and then they'll redo the fits. And they'll produce a new set of ephemeris files which tell you exactly where the position of certain dynamical objects in the solar system will be over a range of dates within certain tolerances. So within these fitting procedures that they use, they don't actually change the planetary masses. They take those as fixed a priori and then just fit for the trajectories of the objects. So it's not just the planet masses it's not just the planets that they're varying here and tracking. They're also tracking thousands of asteroids throughout the solar system. And all of those are important. I think they even track moons of Jupiter and Saturn because, they'll add to the dynamical mass of the Jupiter or Saturn system, and so we have to be sensitive to all of the mass that's in that system. These are differences in the Römer delay for one particular pulsar. And we subtracted out a quadratic because when we fit the Pulsar-Timing model, when we do the analysis, we're removing terms that are linear in time and also terms that are quadratic in time. That takes into account us fitting for the period and the period spin down of the pulsar. And that'll remove lots of low frequency features. So we won't be actually sensitive to very low frequency features, things that are below 1 over the total observation time. So everything here is kind of what's left over after we do this quadratic filtering. And even after doing that quadratic filtering, you're seeing very low frequency trends in the data, in the Römer delays. There's some high frequency stuff still in the DE430 to DE421, but mostly it's low frequency. And it can be quite sizable. So you're dealing with tens of nanoseconds, which is something we have to really worry about because it's comparable to the estimated gravitational wave amplitude. So this is only something that we really came to understand recently, I would say within the last year. And a lot of time has been spent on developing new models to perturb the fits in the JPL ephemeris or indeed any other model of the solar system and try to include this in our Bayesian modeling schemes. Yeah, go ahead. Mm. Yeah. Yes, we can. Or at least we can. The scheme at the moment that we're doing is taking the one version of the JPL ephemeris as a starting point, and then just perturbing certain things, like we're perturbing the planetary masses, we're perturbing the orbital trajectory of Jupiter, and this gives us like Bayesian Pulsar-Timing constraints on Jupiter's mass, which is pretty cool, I think. Because in a way, it's almost like what gravitational wave cosmology does. It bypasses the local distance ladder and gets directly at the cosmology. This is getting directly at the dynamical masses of the planets without going to the the ranging data that have come from spacecraft. So yeah, it's definitely something we're doing. It was done in a frequentist way a few years ago, but being able to do it in our really sophisticated Bayesian modeling schemes, varying all the noise features of the pulsars, searching for gravitational waves, and then also searching for perturbations to planetary masses. It's definitely something we want to do. I think it's pretty cool. I think so. There has been some chatter about trying to look for Planet 9 with the Pulsar-Timing data. The problem is you wouldn't be directly sensitive to it because Planet 9 has an orbital period of something like 10,000 years. So that would just look like a line, which you're going to fit out. So you never get a full cycle. But if that has an impact on the gas giants or the inner solar system, like a knock-on effect, then yeah, if we significantly need to modify Neptune's orbit because of Planet 9, then we might be able to be sensitive to it. People are thinking about it. Many people are saying this. Yeah. Yeah, I mean, it would still be included in the model, but we wouldn't try to. Right? Right? Looking for Planet 9 with a null stream. Put that as a project. Yeah. Yeah. Yeah, what's interesting is that these ephemeris uncertainties, they'll induce a spatial correlation signature which looks dipole. So it is significantly different enough from the Hellions and Downs spatial correlations that in principle you shouldn't conflate them. So if you do a decomposition of the Hellions and Downs curve, you get no content in the monopole and you get no content in the dipole. So the actual dot product of the Hellions and Downs and a dipole term is 0. It's obviously not going to be 0 because it's noisy data. So there's always going to be overlap, and you could mistake ephemeris uncertainties for gravitational waves. So the way we're trying to do this is not really through a stochastic analysis. We're trying to do it, almost like a deterministic signal. So it's actually going back to this kind of model, treating it as in the same way that we treat a single binary or a burst of memory. We actually have a coherent signal model. And there are lots of things we tweak within that model, like the planetary masses. So the reason why we have to worry about ephemeris uncertainties is because different models are currently giving us different answers for upper limits and detection statistics. So this is the upper limit on the gravitational wave background at a frequency of roughly 32 nanohertz. And depending on the particular version of the JPL solar system ephemeris, we get different answers. Now these might look like small differences, but when we're down to the level of 1-ish times 10 to the minus 15, we're cutting into interesting astrophysical territory. Lots of the model predictions for supermassive black hole binaries are around there. And the best constraint we have so far comes from the Australian collaboration, which is an upper limit of 1 times 10 to the minus 15 at this frequency. So differences of 0.2 do matter. And it is rather strange that DE 430 in both upper limits and the Bayes factor looks like the odd one out here. So this is an upper limit analysis. Then this is a Savage-Dickey Bayes factor analysis where we're comparing some common red spectral process to just noise alone. So it's common plus lots and lots of noise per pulsar versus just noise in the pulsars alone. What's strange is that it's not obvious that the most recent JPL ephemeris is the best, because they will weight the data differently or tune the fits depending on what mission they care about. So if they're trying to navigate a probe to Mars, or they're trying to get a good trajectory to go to Jupiter, then they might weight the data differently and kind of sweep anything else that's not directly relevant under the rug. So it's not obvious that DE 436, which just came out last year, is significantly better than 435 or indeed 430. So we don't really know, but there are big differences between these versions of the ephemeris. I'm not going to go through all of these, but we don't really use DE418 anymore. The Parkes pulsar timing array get no red timing noise when they look at their best pulsar. So that's this pulsar is what they use to get the science paper constraint. Now, they didn't actually use DE418. I think they used 421, but it still gives them a very white time series. So the constraint on the gravitational wave background is obviously going to be very, very tight. But this has a huge trend in Saturn that appears to be in there compared to more modern ephemerides. No, what they're saying is that if they're just interpreting all of the red noise that they see in this pulsar as gravitational waves, so it's their upper bound on the gravitational waves, right? Well, they know that there must be intrinsic noise at some level, but this is kind of like the most gravitational waves that could be in there. So you're right, their upper limit is implicitly saying that there's no red noise in there. But it depends. Like when you measure the spectrum of the time residuals from this pulsar, it depends which one of these that you use, which is the troubling thing. But when you compare 418 to 436, you see this huge 30-year trend, which is Saturn. Saturn's orbit and mass has been refined as time has gone on. So as you have been reading, you go on, you make small changes to Saturn's orbit based on newer data from Cassini. Small updates to Mercury's orbit, but we wouldn't be sensitive to that. And the more recent ones are created for like specific missions. So this one was created for Cassini, and it's an incremental improvement to Saturn. And then this is kind of just another update. Mm-hmm. Yeah, because we have most sensitivity to a few nanohertz, then we're most sensitive to Jupiter and maybe the asteroid belt. I can't imagine us being sensitive to like Venus because that's it. Yeah, it's too high in frequency for us to be sensitive to. So you're dealing with the gas giants mostly. Yeah, but the spike at 1 year is because we fit out the Earth's motion. But we could be sensitive to. At leading order, you'd be sensitive to Jupiter's orbit, but you have to take into account sort of the compound effects that Jupiter has on the rest of the solar system. Things like that. So the scheme that we're trying to do is take our current Bayesian model and then tack on an extra ephemeris uncertainty term. So we start off with the basic model, which is deterministic for each pulsar. It deals with the period spin down, interstellar medium effects. You then have some white noise from uncertainties within the radio receivers. You'll have some intrinsic red noise per pulsar, potentially due to rotational instabilities in the millisecond pulsars. And then you might have some common red noise, which, if you correlate it across the pulsars, would be a gravitational wave background. And the idea is that we just tack on this additional term and try to marginalize over any differences between the ephemerides so that it shouldn't matter which one of these we use. It shouldn't matter if we start from DE421 or DE436. You'll be able to perturb away from that solution and kind of marginalize over the differences. So we have a couple of approaches that we're doing for that. One is a physically motivated model where you just have you take that error vector between the true barycenter and the model of the barycenter, and then you just expand that as some Fourier time series and try to constrain the power in that time series. That has not been very successful, so it seems that this is a suboptimal modeling approach. Another is just a straight sort of leading order mass perturbation of the planets. Again, that doesn't seem to connect all of the ephemerides in the way that we want. So you'd imagine that if the only uncertainties were in the planetary masses, this should do the trick. But it seems that there are some small orbital orientation parameters that we need to tweak as well. And another is just this sort of generic dipolar, spatially correlated stochastic signal, which again is suboptimal because it's really a deterministic thing. so those are the physically motivated models. We've also have some kind of phenomenological ones. One is just a rumor mixture model where you take all of the JPL ephemerides, you record all of the rumor delays that they give, and then you have some mixture model which attaches weights to each of the rumor delays, and you see which one the data prefers. So you see which combination the data prefers. I'll show you in a second that that's actually pretty successful, but it is dependent on which combinations of the ephemerides we have, to establish our basis. Now, one thing which I would like to see would be to JPL. I would like them to start off with their most recent fit of the ephemeris, and then just perturb certain parameters and produce lots of perturbed ephemerides and do a principal component analysis to find which effects dominate the fitting there, and that would give us a numerical basis essentially to search over the differences in the ephemerides. They're not on my building, but we have been talking with them. I mean, one of the problems is that, and I understand this problem, it's that they have no real programmatic motivation to do this because they don't really care about where the position of the barycenter is. All they need to know is the relative position of Earth to the other planets because they're trying to navigate stuff there. So, they obviously have a very mission-oriented mindset, so why do they need to know the barycenter? Yeah. Yeah. We could do it all simultaneously. They've even asked us if we can give them some Pulsar-Timing data to help calibrate the ephemeris better. The reason why we want to avoid that is because you're kind of double counting almost, because you're using the Pulsar-Timing data to calibrate the ephemeris, and then they're using that ephemeris to search for gravitational waves. It would be sloppy, I think. I think we could, but it sounds like the format that they do this in. Their data is all in different units and formats, and I've never actually seen what their code looks like, but it seems like a very expensive thing to do. But we've talked to them about this idea of having a fully Bayesian solar system ephemeris. I think that would be really excellent to do, and this is kind of getting part way to that. So you're just starting off with the best fit solution and then perturbing around it. One more recent physically motivated model that we've come up with is it's kind of an expansion of this idea. So we have planet mass perturbations, but we also have tilts of the Earth's orbit with respect to the ecliptic. We also have things like perturbations to Jupiter's orbit, small orbital trajectory changes which seem to make a huge impact, and also drifts in the position of the ecliptic with respect to certain axes. So it's not just tilts, but also sort of a drift as well. This actually does seem to make a difference, and we could be sensitive to this. So this more expanded, physically motivated model with orbital trajectory perturbations as well as planet mass perturbations seems to be the best thing we have so far. So this is showing some tests that I've done on modeling these ephemeris uncertainties. It's on a simulation of some data with the same baseline as the Nanograv 11-year data set. It's just simulating some pulsars with 500 nanosecond time and precision. There are no other processes in the data. There are no gravitational waves. There's no intrinsic red noise. And it's created under the most recent version of the solar system ephemeris. And then you analyze it with the others. So this is trying to demonstrate the kind of spurious gravitational wave features you could get just from the differences in the ephemerides. So these dashed lines are when we analyze under different versions of the solar system ephemeris. So if you create with DE436, you analyze with DE430, you get this quite spurious feature in the posterior distribution for the gravitational wave amplitude. Really, you'd want all of these dashed lines to be the same as the green dashed line, because that's analyzed, produced under DE436, then analyzed under DE436, and you're not seeing any peak in that posterior distribution. But whatever the differences are between the ephemerides are producing these kind of features. So like I said, treating the error in the ephemeris as just a time series that you're trying to model as a power law red process. Doesn't seem to get you there. The solid lines are when we have the ephemeris uncertainty terms in the model, and we're just trying to connect all of the different ephemerides. So they don't actually seem to be very successful when you take this approach. The goal here is obviously to get these solid lines closer and closer to the green, so that you kind of marginalize over any differences. This is when you perturb the planetary masses just in the Römer delay correction. Again, it's getting closer, but it's not all the way there. So the solid lines are getting closer and closer to the green dash line. So you're diagnosing all of these differences in the ephemerides more and more, but still not getting you to where you need to be. And this is the Römer mixture model. Like I said, it's the phenomenological model where you take out the Römer delay that a certain ephemeris gives you, and then you put back in a combination of the Römer delays from all of the ephemerides, and you'll have some posterior distribution for the weight parameters. So that actually does get you there, even if you take out the version of the ephemeris that you started with, so you don't actually include DE436 in your mixture. It does actually still do pretty well. So remember, we want everything to go towards the green dash line. If our mixture doesn't include DE436, you get a bit of a bump here, but it's still pretty good. I don't think I'm going to show it, but the problem is that if you include, say, DE418, which is an earlier version of the ephemeris, in this mixture, then your answers change. So it's very much dependent on what you're establishing as your basis vectors for the search. So this phenomenological model is pretty good if you have a complete set of basis vectors, but the answers can vary. The argument that we're making is that DE418, this very early version of the ephemeris, is so bad, and we've surpassed it with all these more recent ones, that we shouldn't actually include it. So we probably will show this Römer mixture model result in the upcoming nanograph paper. Okay, now these are actually some preliminary results from the real nanograph 11-year data set. Like I showed you before, the Bayes factor for the common red process, which we're interpreting as potentially a gravitational wave signal, varies between 1 for DE435 to 10 for DE430. That's obviously unacceptable. We can't have Bayes factors varying that much between different choices of our models. So it's really crucial that we're marginalizing over these differences. The dashed lines are, again, the posterior distribution of the wave amplitude under different versions of the solar system ephemeris. DE430 is the one that seems to give the strongest spurious signal, and we're not quite sure why, but if you use this Römer mixture model, you're kind of able to get halfway between all of these. You're able to bridge the gap between all of them, and that gives a Bayes factor of roughly 2.5 for a common red process versus just intrinsic noise, and it gives an upper limit of about 1.5 times 10 to the minus 15. And even at the moment, I can't show it because I haven't plotted it yet, but at the moment we're running with the more physically motivated model that I talked about, the one that has planetary mass perturbations and also orbital perturbations. And what seems to matter most would be Jupiter's mass, the tilt of the Earth's orbit, and also small corrections to Jupiter's orbit. So as you'd imagine, Jupiter is the dominant dynamical object in the solar system apart from the Sun. Any small corrections to its mass and its trajectory matter most. So I think I've been really excited about this project because it gives you direct sensitivity to solar system dynamics just as a byproduct of trying to measure gravitational waves with pulsar-timing. So yeah, it's like you said, it's kind of halfway to getting a Bayesian model of the solar system. Mm-hmm. Yeah. Yeah. It is common, but it has a directional dependence, right? Yeah. Yeah. Mm. Yeah. Like the way you're proposing for clock subtraction. Yeah. So how would you avoid that, subtracting some of the gravitational wave background as well? Mm. Yeah. Mm. Yeah, we should check that. Mm. Mm-hmm. So what do you mean for the others? So, oh yeah, well, I think those are going to be subdominant effects. The next thing we would get to in the sort of hierarchy of uncertainties would be the clocks. Yeah. So we didn't realize that we were going to be sensitive to solar system ephemeris uncertainties um, until we were. um, so it's exciting because we kind of predicted this hierarchy of uncertainties. Um, on the solar system ephemeris, we thought was good enough for the time being anyway. But we're now cutting into there, and what's exciting is that that's one of the kind of milestones on the way to mitigation, and then eventually get into the gravitational waves. Yeah, yeah, yeah. True. It's yeah, and we have to rely on these kind of either coherent modeling schemes for the ephemeris uncertainties, or at least if it truly is a stochastic, spatially correlated noise source, we'd have to rely on it having a different signature from the Hellions and Downs curve as a way to sort of isolate it. Um, the good thing is that the Hellions and Downs curve seems to be fairly unique. Can't really think of anything else that gives you that pattern. Yeah, 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 yeah. It's true, true. Yeah, 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 yeah. It's I don't know. I think this is really cool. Yeah, it's just as a byproduct of doing this stuff. It's yeah, yeah. Like in my head, I'm imagining like posterior distribution tracks for the planets throughout the solar system, like probabilistic tracks for the planets from this kind of modeling, which I don't think has ever been done before. That would be neat. That's those are all of the different sort of non-black hole um, signals that we can probe. So it's not just supermassive black hole binaries that we're trying to constrain, although they will be dominant. So that's all I had. Thanks.